Today we will be looking at limits of a function. To begin, let's look at the function f at x equals x squared minus 4 all over x minus 2. We know that when we look at this function here, we can actually go ahead and factor our numerator, which will be equal to x minus 2 times x plus 2 all over x minus 2. Therefore, our x minus 2 are going to cancel out. And when these cancel out, this is going to create a hole. So therefore, we have a hole at x equals 2. So the value of x can never be equal to 2. So we're going to go ahead and graph this. So doing our table of values here, when x is equal to negative 3, our y value is equal to negative 1. Negative 2, y is equal to 0. Negative 1, y is equal to 1. 0, 2, 1, 3, 2, 4. However, that is where we have our hole. And when x is equal to 3, our y value is equal to 5. So we can go ahead and actually graph these points. So on your graph, make sure that you graph each point here. And when you get to when x is equal to positive 2, make sure that you draw it with an open circle. Because recall, when you draw it with an open circle, that just shows that that value is not included. We can connect all of our points here. Pardon me. And include arrows on the end, because this is continuous. So we can see that we have a linear function. So, but what if we really needed to know the value of f at x as x approaches 2? So to do this, we can look at x as it approaches 2 from the left side and as x approaches 2 from our right side. So we're going to look at values leading up to 2 from both sides. So we know that when x is equal to 1, our function is equal to 3. When x is equal to 1.5, our function is equal to 3.5. 1.9, 3.9, 1.99, 3.9, 9, 9. And at 2, it is undefined, so we're just going to put a U for undefined there. When it's 2.001, our value is 4.001, 4.1, 4.5, and 5. So as our f at x approaches our value of 2 from our left side, it is actually going to approach 4. Similarly, as our f at x is going to approach 4 as our x value is approaching 2 from the right side. So since our values are both 4 here, we know that as it approaches 2, it is approaching 4, our whole function. So a limit L exists at x equals a if and only if our limit as x approaches a from our left side of our function is equal to the limit as x approaches our a value from our right side. Otherwise, if this isn't true, other than the limit as x approaches a of f at a does not exist. So example 1, we want to sketch the function f at x. This is again a piecewise function. So f at x is equal to x squared minus 1 for all x less than 1, and 2 plus the root of x minus 1 where x is greater than or equal to 1. After we sketch that, we want to determine the limit of f at x as x approaches 1. So we know that x squared minus 1 here is a quadratic, so it creates a parabola. So we can go ahead and graph this. So this is just our original quadratic function that has been translated down 1 unit. So we can draw or put our points in there first, and then we'll draw our parabola. So we have our points at 0, -1. We have a point at -1, 0. And remember our step pattern, so move over left 1, up 3. So that gives us our value at -2, +3. And at 1, 0, we're going to have our open circle there, because that shows us that that point is actually not included in this function. So that is our part of our piecewise function, which is the quadratic. Next, we're going to graph our 2 plus our root of x minus 1. So when we do this, we know by just subbing in our values, when x is equal to 1, which x in this case is included, our value is going to be 2. When x is equal to 2, our function will be equal to 3. And we could go further on, but 2 points. I like to graph the point at 5, because 5 minus 1 would be the root of 4, which we can take easily the square root of 4, which is 2, so that would be equal to 4. So we would have a point somewhere over here. And then we can connect those points and draw an arrow on the end there as well. So there's our sketch of our function. So now when we're determining the limit of f at x as x approaches 1, we want to look at as x approaches 1 from the left side and as x approaches 1 from our right side. So the limit as x approaches 1 from our left side, we can see here that this is equal to 0, which is this value right here. And as the limit as x approaches 1 from the right side, we can see that this value is going to be equal to 2. And that is just shown right there. So therefore, since these limits are not equal to one another, the limit of our function as x approaches 1 does not exist. These always need to be equal to one another, or else the limit itself won't exist. We're now going to look at evaluating the limit. So part A here, we want to evaluate the limit of x squared minus 2x as x approaches 3. To do this, what we're going to do is we're just going to sub in 3 for our x. So when we do this, what we're going to be getting here is 36 minus 6. sorry, that should have been 3. We subbed in for the x, which is equal to 30. We can also graph this easily too. 4x squared minus 2x, we can factor out a 2x, common factor, and we're left with 2x minus 1. Therefore, we know that we're going to have our x-intercepts at x equals 0 and x equals a half. So for anyone that is a visual learner and they might like to see this, we can see this where we graph our two x-intercepts, and we're going to have our function look something like this. And for part B, we're going to look at the limit of 4 as x approaches 2. Now, for any x value, the limit is actually just going to be 4 itself. Graphically, if we were to graph this, we would have our function here at y equals 4. So for any x value, anytime x is approaching that value, our limit itself will just be equal to that. In our next example here, we're going to look at the limit of 1 over x minus 2 as x approaches 2. So let's just graph this. So when we graph this, we see that we are going to have an asymptote. Okay, so our asymptote here is going to be at x equals 2. And recall there, that is found from the denominator. So we have our asymptote here at x equals 2. And when we look at values, both on the left-hand side of the asymptote and the right-hand side, we come with our graph that looks like this. Again, this should just be review from advanced functions. So we can then look at the limit as x approaches 2 from both the left-hand side and the right-hand side. So the limit as x approaches 2 from our left-hand side of 1 over x minus 2 is actually approaching negative infinity, which you can see as our function is moving down. And as our limit, as our x is approaching 2 from our right-hand side, we can see that our function is approaching positive infinity as it increases and moves up. So therefore, since our limits don't equal one another as it approaches from our left-hand side and our right-hand side, the limit of 1 over x minus 2 as x approaches 2 does not exist. Next, we're going to look at the limit of x squared minus 9 over x plus 3 as x approaches negative 3. Here we can go ahead and factor. So when we factor this, we are left with x plus 3 times x minus 3 all over x plus 3. And when we do this, we can then cancel out our x plus 3. So we'll be left with x minus 3. Therefore, since those actually cancel one another, we have a whole at x equals negative 3. So when we're looking at the limit as x approaches negative 3, of x minus 3, we're just going to sub in negative 3 in for our x value, and we're going to have negative 6. Again, for our visual learners, sometimes we like to see these functions drawn. So if we draw this function here, we're going to have values increasing as you move to the left of our x-axis, our y-axis, sorry, and they're going to be decreasing as you move on the other side. That should be a straight line. Sorry about that. And that's what our function looks like. And if I was able to draw in at negative 3, we know that we would have a hole, and you'd have to include it as an open circle.